Hey, hello, everyone, and welcome to today's ACM Tech Talk. This webcast is part of ACM's commitment to lifelong learning and professional development, serving a global membership community of computing professionals and students. My name is Ethan Giacchetti. I'm an assistant professor in the Department of Computer Sciences at the University of Wisconsin-Madison, where I'm part of the MAD S&P and MAD PL groups. My research uses programming languages and applied cryptographic techniques to design secure systems and build tools to ease their development and analysis. You can find my full bio in the resources section on your screen. For those of you who may be unfamiliar with the ACM or what it has to offer, here's some more information. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. You can see some of the highlights on the slide on your screen right now. The ACM provides access to the ACM Digital Library, which is the world's most comprehensive database of computing literature. It provides leading publications and global conferences that draw top experts on a broad spectrum of computing topics. It provides support for education and research, including curriculum development, teacher training, ACM Turing and ACM, as well as the ACM Turing and ACM Prize and Computing Awards. And also there's the ACM Code of Ethics, which is a collection of principles and guidelines developed to help computing professionals make ethical and responsible decisions in professional practice. Before we get started, I'd like to mention a few housekeeping items shown on the slide in front of you. If you have questions at any time, please use Zoom's Q&A button. We'll organize questions as May speaks and try to get to as many as we can. This session is also being recorded and will be archived. You'll receive an email notification when it becomes available, and check learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentation, you'll see a survey pop up. Please take a minute to fill that out and help us improve our tech talks. So today's presentation is Programming with Distributed Systems with May Milano. May Milano is an assistant professor at Princeton University, and she works at the intersection of programming languages, distributed systems, and databases. Her work has appeared in top-tier academic venues and has attracted attention from the Swift language team. She's a recipient of the National Defense Sciences and Engineering Graduate Fellowship and has won several awards for her writing and service, and is a founding member of the Computing Connection Fellowship Selection Committee. May, without further ado, take it away.
Awesome. I'm assuming you can hear me. Just give me a nod. Great. Sharing my screen. And that should be all right. Thanks for that wonderful introduction, Ethan. So today I'm here to talk to you guys about programming distributed systems, which is the center of my research. And let me start by saying that programming distributed systems, oh goodness, is hard. Modern applications, things that used to run on a single thread of a single machine, like say an office suite, have become concurrent or distributed or even geo-distributed. What would once have been a local single-threaded application has become huge. I can't even sign into a word processor these days without using at least one cloud service. And as our systems have scaled, our ability to program them has not kept pace. The results are predictable. An endless parade of bugs and vulnerabilities as programmers wrestle with each new leak in what were once reliable abstractions. This is where we are today. We've built a cloud and it's wonderful and it works and it's how I'm talking to you today, but we still don't really know how to program it yet. This is where my research has come in. In my work, I've talked about how to solve things like destructive data races, handle sources of coordination overhead, and even deal with consistency on geographic scales. But before I can tell you about my cool solutions, I should tell you a little bit about the problems. In particular, what did I mean by a data race? What are the sources of coordination overhead I'm worried about? And what even are consistency errors? All right, let's start with the data race. So a data race occurs whenever two or more threads simultaneously attempt to access the same piece of memory and at least one of those threads is a writer. The classic example of a data race is a split increment. In this example, two different threads are simultaneously attempting to increment the same value. What winds up happening is that when one thread reads the value and prepares to do its write, the write of that gray thread may wind up erasing with the read of the orange thread. It's literally a race. It's non-deterministic whether the orange thread will see the number that was previously in the memory or the number that is being written to memory. If the orange thread loses the race, the result is basically a lost increment. After both of our threads have run their operation, we've gotten out the number 6 when we really might have expected the number 7. This particular data race is an example of a destructive data race. Assuming the programmer meant to increment twice, this is an example of some non-determinism due to concurrency, which causes an error in the program. This is also pretty standard. It's the sort of thing we've known about for as long as we've had threads simultaneously accessing memory. And there have been many ways to solve it in the past. One particularly popular way, especially in the world of databases or distributed systems, is to use transactions. Transactions are an amazing abstraction that provides this idea of atomicity. It makes it so that all of the gray thread or all of the orange thread will appear to execute exactly at once, and they can no longer interleave. And it solves the problem in databases. But it's not the perfect solution, and in particular, it's quite expensive, especially in shared memory contexts. But let's put a pin in that. We'll come back to it later, and for now, we've defined what our data races are. Now let's talk about what kind of consistency errors I'm worried about, and in particular, how that leads to coordination overhead. So when I'm talking about consistency for this talk, I'll be talking about the analog of memory consistency in a distributed replicated storage system. In this kind of system, individual databases are copied so that clients can communicate with any of the copies of the database and still believe they're communicating with the same single centralized system. In this setting, a consistency model is the set of rules that govern what should happen if I perform a write at one replica and then later perform a read at some other replica. The strongest consistency model that we'll consider today is called linearizability. Under linearizability, if I perform a write at any replica, I wait any amount of time, and then I perform a read at a different replica, I'm guaranteed that the effects of my write have propagated to all replicas before I perform my read. This is sort of the gold standard in consistency. It allows people to pretend like there were never copies at all, and we only ever had one centralized database. It's also somewhat hard to implement efficiently and tends to be best used when deployed on small scales like islands, like say the Greek island of Paxos, using protocols that have been long established for consistent replication, like say the protocol of Paxos. And this is actually going to be our source of coordination overhead, is handling replica synchronization. Now let's talk about consistency errors. See, while we can still make consistent replication work and work really well at relatively small geographic scales, things become fundamentally more difficult at global scales. Once you've replicated around the world, you have to contend with some unfortunate physical realities. The speed of light, as it turns out, is surprisingly slow. It's only about 4 inches per clock cycle on my computer, and it might be even slower on yours. At this kind of scale, we've quite literally outgrown Paxos, much bigger than the island or the protocol could ever support. And we'll have to accept the fact that replicas will temporarily diverge. The question is just, how do we handle that? And some databases have taken the approach of passing this divergence on to the programmer, giving a series of guarantees that collectively are called just weak consistency. Under weak consistency, if I perform a write at some replica, and then I wait any amount of time and perform a read at a different replica, I might see a historic value. While I'm guaranteed that my write will eventually propagate to all replicas, I don't really have any time estimates on that guarantee. My reads might see a value from today, but it might see a value from yesterday, tomorrow, sort of leaving programmers wrestling with this time travel behavior. In fact, some database designers have embraced this, naming their databases after time machines. If you're not familiar with the blue box on the screen, this is where they used to put criminals temporarily in London in the 1960s. It's also a time machine from a television show. And it's hard to program against. Not the criminal supplying thing, the idea of time travel databases. So that'll be our primary source of consistency errors. Now we've got our definitions. Let's dive into our solutions, starting with the largest scale first, handling consistency errors. And I want to start off with an observation that there are some applications that'll work absolutely fine under arbitrarily weak consistency. Consider, for example, that I'm running an online game service. I'll want to do things like record wins and losses of players, perform a matchmaking service where various players get matched to opponents of the correct skill level. And I might want to run some tournaments where, say, I invite the best 10 players in the world to duke it out for fun and glory. I would argue that recording wins and losses is actually kind of okay with weak consistency. If I'm playing Super Smash Bros. Online against all of you at once and I win, I don't necessarily need for the entire world to know about that instantly. I'm kind of okay if somewhere in Brisbane, they take a couple of minutes to see that update from me. Other things, though, will need much stronger consistency. For example, if I'm going to run a tournament where I invite the 10 best players in the world, I really ought to actually get the 10 best players in the world. I built a new programming language called Mixty exactly for this kind of application in this domain. Mixty is a transactions language, which lets you write distributed transactions over traditional distributed databases, in which the transactions run as quickly as possible, and therefore with as little consistency as possible, while still satisfying programmer supplied invariants, expressing their consistency needs. Let's take a look at how this works via our example. Oh, and if you want to look up the paper is from PLDI 2018. You can find it on my website. Okay, here's our example. So we want to record some wins and run some tournaments in an online game service. So what are we going to need? Well, we'll need a table to store our wins and also to store our losses. And we'll also want a table of rank, which will store the players in the world ranked by how good they are. So rank number 1 player is the best player in the world. Rank number 2 player is the second best player in the world. There is no rank 0 for now. We can also have some transactions that will manipulate these. For example, we might have this match transaction, which takes 2 players, records that one of them has won and one of them has lost. We also might have this invite to tournament transaction, which will initialize an empty list of the best players and go through the first 10 players in the rank table, add them to the list, and then return that list. I want to pause here actually and say that in this presentation, all of the code that I'm putting on the screen is pretty realistic. I'm not leaving out any annotations or oversimplifying an example. There's no secret programmer hints that are missing. This is roughly what you would write as a programmer today using these kind of tools. I've also tried to make that mean it's pretty accessible to standard programmers with a background in, say, Java or C++. So when I put code up, I'm going to wait for a little bit of time and vamp and say some words like I'm waiting for a little bit of time after I put the code up, so that we all have time to read these examples. Okay, now that I've given you time to read these examples, let's go back to the presentation. So we've got these transactions for matches and inviting the tournament. And one thing that's unusual here is that we've added these words weak and strong to the transaction headers. These are hints provided by the programmer. They tell Mixty what the programmer's expectations of these transactions needs are. Mixty will read these and analyze the transactions to discover, well, we should put the wins and the losses on a weakly consistent storage, and we need to keep the rank on strongly consistent storage automatically. So far, so good, but also pretty standard. This basically matches what a traditional database would do if you set an isolation level for a transaction. Where Mixty really shines is recognizing that consistency composes across transactions. Consider, for example, this much larger transaction, calculate rank, which is going to use the wins and losses information to rebuild the rank database. Here's what we're going to do. Oh, I see that I've got our coordinator on video, so I want to quickly pause and make sure there's no problems. There are no problems. Excellent. Back to the calculate rank transaction. So what we're going to do is we're going to start by initializing a list of win-loss ratios that we'll use to store temporarily the wins and losses as a ratio for use in our rank table population. We're going to then loop over all the players in the entire world, divide their wins by their losses, and then add that to the win-loss ratios list. Then we'll sort that list by the win-loss ratios, and we will then extract the player component from that sorted list and use it to repopulate the rank. That complicated bit in the middle there, sometimes when I promise real code, it's double-edged sword. All it does is say, discard the ratio, keep the player name from the list that's been sorted. So this code has a bug. In fact, it has 2 bugs. I'm going to give you all a few seconds to spot it before I tell you what the answer is. Well, the first and most obvious bug is probably the one inside the for loop. We're dividing the wins by the losses, and sometimes there are undefeated players, so we might have a divide by 0 error here. That's a real bug. I left it in because if I fixed it, it would wind up overflowing the line, and then it doesn't look as nice. There's, however, also a more important bug, which is a consistency bug. See, while this transaction will run atomically on a single replica, it's important to think about what replica it is that it's running on. And in particular, it's going to wind up running on one of the weakly consistent replicas. When we run this calculate rank transaction, we will see an atomic vision of what one of the weakly consistent replicas is looking at, not necessarily all of them. When we then use our calculated rank to run the invite to tournament transaction, creating the list of tournament invitations, it will run with strong consistency and it will run at a strongly consistent database, but by then it's too late. The rank information it's using has already been tainted by weak consistency. So what we're going to wind up getting isn't the 10 best players in the world, but rather just the 10 best players in the replica that the calculate rank transaction ran on. We're also going to get a bunch of angry emails from users that have different local replicas and therefore think that they must be among the top 10 players of the world. And if there is one thing we must avoid in our online game service, it is receiving angry emails. What's happened here is a violation of a sort of intuitive property of applications that mix consistency models. In particular, that strong outputs should always stay strongly consistent, or more formally, that strongly consistent observations, things like the invite to tournament transaction that have been annotated strong, should not be influenced by weakly consistent operations, like the vaguely synchronized wins and losses tables. Mixed as a programming language is able to recognize this at compile time, determining the improper influence within the calculate rank transaction and kicking it back to the user, telling them, hey, there's an error. And we're going to dive into exactly how that happens. But before I do, I should say that I've been simplifying things a little bit more than I perhaps should have. So far in this talk, I've been saying things like weak consistency and strong consistency to basically mean eventual consistency, that things eventually will replicate for a week, and linearizability, that things obey wall clock time and have a distinct order for strong. But in practice, there's actually a whole lot more consistency models out there. The TARDIS database I use as an example is, for example, causally consistent, not even eventually consistent. And there's a whole lattice of consistency models in the world, the vast majority of which are either strictly weaker than linearizability, are both strictly weaker than linearizability and strictly stronger than eventual consistency. This order also allows us to define a really formal and crisp definition of what it is to have improper influence to violate that strong must stay strong property. And in particular, improper influence is guaranteed to occur when a less consistent right, so something up in this diagram, influences a more consistent right. Sorry, yes. Something down in this diagram. It also occurs whenever two things that are incomparable in this diagram would influence each other. And our insight is that we can prevent this kind of improper influence by use of an information flow type system. A type system that's commonly found in the security literature, where it's used to protect data integrity or the confidentiality or secrecy of data. Okay, with this in mind, let's go back to that calculate rank transaction and see how MXT is able to track the information flow and determine statically that there is an error. So first we start with ground truth. From the other transactions in the system, we know that the wins and losses have already been stored on weakly consistent systems, and that the rank has already been stored in a strongly consistent table. We can then statically see that the wins and losses flow to the win-loss ratios list, which allows us to label the win-loss ratios and everything derived from it as weakly consistent. We then later see that we're assigning the rank table from a read of the win-loss ratios table, which drives a contradiction. Because the win-loss ratios flows to the rank, it gets the same consistency as those ratios, which is no stronger than weak consistency. But we've already told you that rank was strong, and that was our ground truth. So we can signal this error directly to the programmer. And that's what we do. But a programmer is not without recourse. There are, of course, ways to run online tournaments and game services. And MXT recognizes and allows us for that as well. In particular, and this is one place where we really have a distinction between our analog insecurity and inconsistency. Many weakly consistent systems support some abstraction that allows them to temporarily become consistent, to say, pause the world for a bit and let everything finish synchronizing, or to just perform a read at every single replica in the world so that you're sure you've seen every single piece of traffic. This sort of universal quorum is something our hypothetical database exports and allows. And MXT allows for the people who write programs to use these database exported operations, and internally knows that it corresponds to a more consistent operation despite coming from a less consistent database. With that information, MXT, seeing a quorum of everyone, is able to statically determine that everything here has the effect of strong consistency for the instant of the calculate rank transaction. What's interesting here is that the dynamic mechanism at the heart of this, the idea that you can do an actual consistent read temporarily, has a lot of similar vibes to things like a declassification in security, but has a very different root of trust. So if there's questions about that later, I'm happy to go into the differences. Our type system really just works in these examples. We're able to find the errors, report them back out, and there's an easy patch. But it also just works on even more. For example, you might want to read something that's strongly consistent and use it to affect something that's weakly consistent. And that's always fine. That's something that has extra guarantees you didn't need. For example, if I wanted to respond to my invite to tournament transaction by sending a bunch of email to various people, that would be fine, and MXT would allow that. So what have we learned so far? By preventing improper influence via information flow type systems, our new programming language MXT can give you reasonable semantics for mixed consistency transactions. In particular, a strongly consistent observer will only ever witness strongly consistent behavior from traces. I should also say at this point that while MXT is primarily a programming language's contribution, it's also a system, not just a language. Like everything you'll hear about today, it's real and it's implemented and you can go use it. In particular, we implement it as a deep embedding into C++, doing far too much magic with templates. It's built as a shim layer atop existing databases, and it has some cool systems components in it, like an ability to synchronize mutually unaware non-compositional consistency. It's implemented in about 15,000 lines of C++, and you can go use it and download it today. But I should warn you, It's implemented in about 15,000 lines of C++, so it might take a minute or two to get it to compile. So Mixed answers a lot of exciting questions about how to handle mixed consistency transactions. It says, you give me some annotations and I'll make sure that you're respecting them. But it doesn't answer an important question at the heart of that. Where exactly did these annotations come from? How was the user able to determine that they were correct to say that the wins and losses can have weak consistency and the rank has to have strong consistency? To put that a different way, are we able to statically or programmatically identify a class of applications that are always going to be safe under weakly consistent replication? And that is the animating question for the next section of the talk. I want to talk to you about ensuring reliable observations for building correct code under weak consistency. So, what's a reliable observation? This isn't some technical term that you've forgotten from sophomore year of computer science. It's a term that I kind of made up for the purposes of this talk. But for this talk, a reliable observation is some sort of read, some sort of observation of state that comes with a guarantee. For example, if I run a transaction, a strictly serializable transaction, and I perform a read of state in that transaction, I have the guarantee that for the duration, effective duration of that transaction, the value that I read actually reflects what's on the database. It's a time-boxed, dynamically enforced guarantee, provided the transaction doesn't abort at least. But there are some other things that are guarantees that don't have that flavor. For example, when I was talking about my online game service, I might have observed that the wins of a particular player was at least 15. That's a reliable observation. And it's a reliable observation because we've seen all of the relevant code in the database. And there's nothing that can possibly falsify the statement. If I've seen that you've won at least 15 games and my replica's 4 days behind, then at worst, you might have won even more games, but you'll still certainly have won at least 15. This is a predicate that's stable. When it becomes true, it stays true, and no concurrent mutation can violate it. It points out to a more general observation that the more we restrict the mutations, the more we know about how the state in our program changes, the more general the observations we can make about that state. There's sort of a spectrum. On one extreme, we have things like constants, where we can have arbitrarily weak replication. We might not synchronize for years, but every observation will still be correct because they're a constant. Ever since Python 3, if I read true, it'll stay true tomorrow. That was a joke about Python 2 allowing you to set constants to arbitrary values, which is a bad design, and it should feel bad. On the other extreme, we have things like single writer or multi-writer registers, where the instant I read it, no matter how consistently I read it, there might be another writer that's come along and just destroyed everything there. That's completely reset the value. So it's pretty much impossible to have any reliable observation in the absence of a dynamic enforcement. But there are some useful things in the middle. Things like counters that are only ever incremented, or sets that are only ever added to. This is a collection of objects that grow monotonically. They get bigger. They've got some natural order, like less than on the integers or subset on the sets, and they'll always get bigger with respect to that order. And this set of objects supports a particular kind of stable predicate or reliable observation, a threshold observation. If you compare it with a constant, and it's bigger than that constant, it'll stay bigger than that constant. In other words, if all the shared objects in my system only ever grow, and we only observe thresholds or some stable constant characteristics, then your program can be correct and even convergent under weak consistency. And as a bonus, none of this stuff requires any coordination at all. So we've avoided all of those sources of coordination overhead we were worried about in the beginning of the talk. It works. It's extremely useful. But of course, it feels a little bit limited. And it does pose a pretty major question. Can I actually build something useful out of counters, sets, and similar other related objects? Good question. Surprisingly, yes. As it turns out, many core system components are fundamentally monotonic. And rather than take my word on that, we went ahead and built the system out to prove it. I should also say at this point that that monotonicity result is not due to me. It's due to a bunch of people for going back years, especially in the databases community. Where my contribution really comes in is the demonstration of utility, the building of a big system whose core is monotonic. The system we built, Duratio, is a state machine replication system. Remember right at the beginning of the talk where I talked about a database that gets replicated, so there's lots of copies and that fundamentally they need to stay synchronized? State machine replication is the most common way to handle that. It lets you take a single computer, clone it a bunch of times, but still look to the outside world like there's a single machine, so that each of the clones is a perfectly synchronized state machine. Our solution for state machine replication beats the state of the art. In fact, we benchmarked it at being about 10 times faster than Zookeeper, a system in a similar space. And it's real. We've taken it to systems conferences. We've done a tutorial at SOSP. We've sent posters and papers various places. And it's currently being used to build successor systems like Cascade and the Duratio DDS. And at the very core of it is monotonicity. Also, if you're looking for papers about this, the original Duratio paper is from the Transactions on Computer Systems in 2019. And a particular paper focusing just on the monotonicity part is from the SSS workshop last year. So let me show you where the monotonicity is at the core of Duratio by talking about a particularly important protocol that's at the core of any stable state machine replication system, in particular, stable message delivery. So how does this work? Well, in a state machine replication system, we have to make sure that all messages received at any replica are forwarded to all replicas reliably. The usual protocol for this is a message arrives at a machine, say A. That machine then forwards that message on to everything else like B and C. Those machines then generate an acknowledgement and send them to everyone in the cluster. Once each machine has gotten an acknowledgement from everyone in the cluster, that machine knows that the message has arrived everywhere in the cluster, and so it can consider it delivered, and it knows that no failures or network partitions will threaten that particular message's delivery. In Duratio, we implement this in a monotonic domain-specific language built atop a simple monotonic data structure called a shared state table. In our shared state table, columns correspond to individual data types, and rows correspond to the view of that data type at a particular machine. So the top left of this example would be the value of X at A. Cells will only contain monotonic objects, like counters or sets, and our custom DSL enforces that they're only ever updated by inflating them, and they're only ever observed by comparing them to a threshold or by running some other monotonic function on it. Our custom DSL, by limiting you to a small range of combinators, ensures that all the programs you build compositionally on this will be monotonic. One of the nicest things about monotonicity is it's a very compositional property. So let's look at stable message delivery in terms of this shared state table. So to start off with, we got a message at A. So A will mark that it has received a message from itself in its table. Then that message will get sent to B and C, and they will turn around and mark that they've received a message from themselves in this table. In the background, a process at all replicas will be running, checking to see if the minimum of the received from A column is at least 1. Minimum is a monotonic function. We're comparing it with 1, which is a constant. So this is a stable predicate, which means that we're able to deduce with full consistency that it is true when it becomes true. Simple, but I promised that we would be avoiding coordination overhead, and what I just kind of did was throw a big centralized table at you. So in practice, there isn't a big centralized table. there are a bunch of replicas of this table at each individual machine. Let's rewind and see how this works now in the context of the replicated shared state table. Once again, a message arrives at A and we mark it as having been delivered there. And once again, we send messages to B and C, and now they mark it as having been delivered in their replica of the overall shared state table. At this point in the protocol, everyone's running this minimum column is greater than 1 or greater than equal to 1 in the background. But for now, that's false everywhere because none of these replicas are precisely synchronized. And that's okay. It's just going to block until that becomes true. Because we know that in the background, all of this information is being eventually replicated. And once it's actually arrived everywhere, this minimum operation will become true and we'll be able to mark the message as delivered. Same exact protocol as we had before, but implemented in terms of monotonic state. Using simple tricks like this, we were able to build 95% of strongly consistent consensus atop a weakly consistent data structure. And because we relied on monotonic state, and we had these strong previously proven properties about monotonic convergence, we got race freedom, we got convergence entirely for free. It's really a perfect example about how careful language design can build better distributed systems. And as always, it's real. The main Duratio project website is at duratioproject.github.io, and the team behind Duratio has some more work coming out soon that will probably link to the website when it arrives, but keep your ears and eyes open. So Duratio is very impressive. But of course, ultimately, not everything really is monotonic. There will be sometimes that 5% of consensus that wasn't in the 95%, where you really do need to rely on something other than monotonicity for your coordination. Remember this slide, where I said that when you have to deal with races, you can use transactions and that'll solve races in a distributed system? I told you that that was kind of expensive and somewhat dangerous, and I had to put a pin in that. Let's take that pin out now and talk about our last section of the talk, returning to the world of shared memory for a local computer with our last paper. I want to talk to you about a recent work that appeared at PLDI in 2022 on a flexible type system for fearless concurrency. What this work is going to do is statically eliminate all destructive data races at compile time. If the compiler compiles your program, then you're never misusing locks. You'll never race on unprotected memory. You will never have that kind of Heisenbug to debug again. What our type system is going to basically enforce here is mutual exclusion. This is a setting where memory is divided up. Some memory is private to individual threads, and a lot of memory is guarded by locks, a dynamic mechanism. In order to access the memory that's guarded by locks, you perform some sort of dynamic call that temporarily assigns the memory the lock guards to the memory that you can write. This is locks. This is how they worked for years. And it's not that hard to do. We've got operating systems primitives for introducing locks and for acquiring them. The programming language challenge isn't in doing that. It isn't in implementing locks or implementing lock acquisition, but rather it's in releasing the locks. See, while our gray thread has held the gray lock, it might have formed references between the objects that the gray thread naturally owns and the objects that the temporarily gray lock guards. And that's fine. The whole point of acquiring a lock is to be able to modify the data that that lock guarded. But it does pose a bit of a challenge. When we release the lock, and the lock is no longer gray, the guarantee we need to enforce is that the gray thread will not attempt to use, not attempt to read, not attempt to write, not attempt to use at all, anything guarded by the lock. And in order to do that, we need to know where these references are. We need to understand which references can be used and which references can't. And unfortunately, tracking pointers in a shared memory system like this, like a traditional C style pointers and concurrency system, is undecidable in general. But that's okay. I'm a programming languages researcher. I solve undecidable problems for breakfast. And this particular undecidable problem has been solved many times, most popularly perhaps by Rust. Rust has a surprisingly elegant solution. In Rust, the type system enforces that there is at most one inbound reference to every single object, in particular, every single locked object. It follows a principle of ownership, where it's really clear to track exactly which thread or lock owns which individual object. And it turns out to be much easier to track the one reference that goes into a locked region rather than track the arbitrarily many references that go into a locked region. There is, however, a limitation with Rust's ownership pattern, with Rust's decision to just keep everything to be a tree. As it turns out, not every data structure in the world is a tree. Consider, for example, a circular doubly linked list, a common data structure we've learned about in undergraduate computer science curriculums for decades now. It turns out it's very hard to write such a data structure in Rust. If I wanted to, I would go and Google about to see what's the best way to implement it, and I'm sure I'll find information about that somewhere. And once I've Googled enough, what I will discover is a bunch of people telling me about the stacked borrows paradigm, some other folks saying that these libraries have been proven correct in a theorem prover and therefore we can use them. Some other people saying unsafe isn't really a bad thing. You can use unsafe, it's fine. But if I want to stay in safe Rust, I'll wind up with something like this. This is terrible. I mean, I didn't syntax highlight it, and maybe the font's a bit small, but the actual code isn't great either. Each of these layers of types that we've wrapped the next and previous pointer in will add runtime overhead, tracking information that we fundamentally from the data structures and variants don't need to track because we already know it. Or it'll add layers of complexity, forcing you to perform unboxing and reboxing steps to access things. And ultimately, it's going to wind up doing exactly what those people on the internet told me to do. It's internally using unsafe. It's internally ensuring things follow a stacked borrows paradigm. It's internally proving things in theorem provers. We can do better. One keyword, no default runtime overhead. Pretty natural looking code. So how did we do this? What's the fundamental problem that we solved that Rust opted out of? Well, it's something that I like to call path confusion. Something that occurs when two syntactically distinct paths, like A.B.C versus A.B, might or might not point to the same object. And it's a property that turns out to be impossible in trees. Let's look at this property in terms of a circular doubly linked list. Now, I've illustrated the list with code and pointers and arrows. Here we've got a list node, which has a next and a previous pointer pointing to other list nodes and a payload. The blue pointers along the spine of the list here are those next and previous pointers. The red payload pointers connect the object stored at the position in the list to the list node struct that is used to navigate to it. You'll notice that there's red pointers and the ISO keyword on this payload. ISO in my language stands for isolated. It means that there's at most one inbound reference that can get to that payload. So it's the place where an ownership-like thing winds up showing up. Let's look at some code that works through this list. First, it's going to point a temporary pointer on the stack to the head. Then it'll make a temporary pointer to the second element. Then it'll send the head's payload and the second element's payload to two different threads, and then it will exit. The thing that our type system needs to do is decide whether this code is safe, whether it will ever involve a potential data race. And for this example, it actually looks kind of okay. As I've illustrated it, it's taking two different payloads. We know that they're distinct because of that isolated pointer guarantee. It's sending them to two different threads. What could go wrong? Well, a lot, it turns out. Because while the diagram that I've illustrated here is a valid instance of the linked list data type, This diagram is also a valid instance. I never said that next and previous had to go to different places, or that in particular they couldn't go back to the same node. Under this instance, our head and second pointers wind up pointing to the same node. So while we still have the guarantee that every payload is targeted by at most one reference, that doesn't really help us because head and second are the same. So we're just following the same reference twice to get to our two payloads. Our bug here is that we wrongly assumed that head and second would be distinct. And we used that to wrongly assume that their payloads would therefore be distinct. This is path confusion. This is the sort of thing that comes up when you start to allow any non-tree data structures in your language. So how do we solve it? Well, we basically restore a type level version, a type level abstraction of those Rust trees. See, when our compiler looks at and sees this data structure, it doesn't just see this data structure. It also sees this one. What we wind up doing is treating all of the pointers that are not isolated as though they might go to the same object, creating this big orange blob, this entire region where all the objects might or might not be the same. In this sort of region level view, our isolated keyword becomes the only kind of link in the graph. It establishes our boundary between various regions. Using this, we're able to simultaneously look at code in this form, code in this form, and code in this form. And we allow programs to type check only if their behavior is obviously correct under all three views. One consequence of this is that if you want to avoid runtime overhead, you'll wind up discovering that all of your regions are shared as a unit, that it's very hard to concurrently operate on the next and previous pointer, since statically we don't know that they're different. However, if you're willing to accept some dynamic overhead, we can fix that too. In particular, if I'm going to correctly run our code example where we send the first and second element off to different threads, I would need to check to make sure there are at least two elements. I can use this if distinct keyword here to do that check, where if I run if distinct head and second in the true branch, I know that there are actually two different objects for the head and the second, which in turn means, because the payload has that isolated keyword, that there are two distinct payloads. So my code is now actually correct as written, as long as I have this dynamic check-in. And it's a cheap check, it's just pointer equality. More importantly, it's exactly the check you'd need to write the code correctly in any language. We can also have a more intensive check. For example, this if disconnected thing. What if I wanted to split my list fully in half and send the first half and the second half of the list to fully different threads? Well, in order to do that, I need to make sure that not just the head and second were distinct, but that they rooted fully distinct object graphs, that there was no path from head to second or from second to head. The automatic if disconnected check will do this in our language. Under if disconnected, when we're in the true branch, you'll wind up having two completely distinct regions rooted at the head and the second, which allows you to treat them independently and concurrently no matter what you want to do. You could send the entire head list off and the entire second list off. We know they're different. Using features like these, we've been able to implement fully featured collection libraries, including many basic collection operations that are impossible to implement under safe Rust, and other collection operations that are difficult or impossible to implement under competition languages. It's another example of where careful language design can make it easier to write correct systems. And this particular one has taken the form of a Swift proposal. We've posted it on the Swift forums, we are collecting comments, and we're fingers crossed, looking forward to seeing it in a future version of Swift. So that's all I really wanted to talk to you about today. We've seen how to solve problems at every scale, from handling consistency errors in geo-replicated systems without introducing coordination, to handling traditional memory concurrency without worrying about dynamic data race bugs. And with that, I'm going to leave you. Before I do, I should say thanks, and this takes a village. Every single paper I talked about today has co-authors. And there's so many people out there who've helped me despite that. Or not despite that, who's helped me without even co-authoring a paper. So I am here as a face of thousands. Thanks again, and I will take questions.
Great, thank you, May. Let's move to the question and answer. The first question I want to bring up, we've got a ton of questions coming in the Q&A. Thank you, everybody, for those. The first question is that many distributed systems are built using communication protocols, things like HTTP or over RPC or things like that. Can you use mixed-T-like semantics? Can you enforce mixed-T type guarantees in those sorts of situations?
Yes, actually, the protocol is really independent of the guarantee. So when I write a mixed-T style application, I don't have any opinions about what exactly writing or reading does. It could be send an HTTP request. It could be have a whole SSL handshake. What matters is that it's some duration of operation, some duration of protocols that at the end has produced a value. The guarantees we're getting are across various invocations of operations. So it would tell you if you used HTTP to retrieve a piece of information about a web page, it'll tell you what it's safe to do with that piece of information. Could I then make a put request to put it somewhere else? Maybe. Depends on whether I've said it needs to be consistent and whether I said it was consistent when I read it.
Cool, thanks. The second question that we have here is for Duratio. Are there any underlying assumptions about the distributed system guarantee needs to guarantee things like message delivery and doesn't suffer from partitions and things like that?
For progress, absolutely. Under any monotonic solution, any monotonic DSL, what we're going to be able to guarantee is convergence in the presence of progress. We can't guarantee progress itself. In particular, when we were looking at that fun little example here where we were sending all of our messages around, if I had a partition in between the messages arriving and the stabilization of the SST might just never stabilize and the system would grind to a halt. Liveness is important, but it's not monotonic. It has this flavor of something eventually stops getting bigger and gets smaller again. So it requires some amount of non-monotonic protocol design, which means you have to, once again, get convergence through difficult manual effort. When I said we can do 95% of consensus, that's kind of what I meant. That 5% is left in handling things like unrecoverable partitions or unrecoverable failure.
Cool. Let's see.
And to be clear, we also do implement that 5%. We don't just kind of leave it on the table. We just don't get it for free from monotonicity. So a question that has a lot of upvotes here is I think this came in very early during the mixed-T session, during the mixed-T section rather. Could the same sorts of abstractions that you're building and using in mixed-T, could those be reached with attributes or directives to an existing language instead of having to implement something totally new, something like macros in Rust or OpenMP like directives in C++? Sort of. So I should mention that mixed-T is embedded in C++. Like there's no separate compiler to download. It's just entirely written as templates on C++. But the trouble is the interaction with the basic language primitives is not immediately straightforward. See, the premise of monotonicity is when something is true, you get to react. But when it's false, it's not really false. It's just not true yet. So if I were to read something from a database in mixed-T and I were to take that value into like raw C++ or raw OpenMP or any raw language with a conditional statement, and I was going to write if predicate, then block, else other block, I've already broken the model. Because the else block, which executes when this is false, technically doesn't know it's false. It just knows it's not true yet. If you wanted to, with a careful hand, you could build a library that interacts with the control flow by basically reinterpreting things like else or things like negation as we're not sure instead of it's false. But my fear is that would lead to significant programmer confusion. So sort of you could add it, but you wind up re-implementing these control flow structures in sort of a DSL or a macro. And telling programmers never use the built-in conditionals, never use built-in negation, don't even use short-circuiting and. use the ones the DSL provides. And that's what we did for MXT. That's how it's implemented.
A question here about monotonicity, about the monotonicity. You used monotonicity for the example you gave involved counters, where you're just trying to hit some threshold or something like that. And this question is asking if you can do this for more general data structures where the states are only partially ordered, but operations still lead to some subsequent state in that order.
Absolutely. As long as you have a lattice, which is to say, as long as there's a distinct way to take two reconciling states and find the least upper bound of those states, this will work fine. A perfect example of this is vector clocks. Vector clocks are, the whole point of them is partially ordered. They still form a lattice. I can find the least upper bound of two vector clocks by just taking the maximum across every entry in the pair. I can find the lower bound by taking the minimum across every entry in the pair. And all of the techniques we talked about that rely on monotonicity will work really well for these data structures. So anytime you can take a state and embed it in a lattice, you are guaranteed to be okay. Another example of that would be sets. Sets famously partially ordered as well. The set with the green element and the set with the blue element are not comparable. But if I take the set with the blue and green element, it's bigger than both. And if I say take the empty set, it's smaller than both. Next question, please.
Yes, sorry. So there's a sort of technical question about how MXT works in the example that you had with quorum reads. In the quorum reads with the wins and losses, are you getting a consensus, a quorum consensus for an individual value, like the number of wins or the number of losses at each, of each local copy? I see. Are you doing this? Are you getting the consensus at each copy, or are you only getting the consensus at one location? I think is the question here.
So MXT is a shim, which means that whatever the underlying data store supplies is what you can export. In this sort of hypothetical data store world, what the quorum read is implemented as doing is putting up a barrier for writes. So the system, all the replicas will reject writes, then just waiting for a synchronization and reading at a single replica. But it would be equivalent if there was a way to merge the replicas in general to just read from all the replicas and do that merge at the client side. The one guarantee you need to have, because this is still a transaction, is that for the duration of this sort of merge and read operation, there aren't additional writes coming in that will wind up ordered before the transaction. As long as additional writes coming in get ordered after the transaction, you're all set. And ultimately, MXT is not trying to innovate on this particular technical mechanism. It's trying to take advantage of the fact that existing databases have innovated on it already and will provide already a way to do a more consistent read temporarily.
Great, thanks. We still have more questions, but unfortunately, I'm afraid we've run out of time for today. So I'd like to thank May again for her informative presentation and insightful answers to a bunch of questions. Special thanks to everyone who attended for taking the time to participate today. This talk, as a reminder, this talk was recorded. It will be available online in a few days at learning.acm.org. You can find announcements and upcoming talks and other ACM activities at learning.acm.org and acm.org. Also, as a reminder, please fill out the quick survey where you can suggest future topics or speakers, which you should see pop up in a moment. So on behalf of the ACM and May Milano and myself, Ethan Cicchetti, thank you again for joining us, and I hope you'll all join us again in the future. This concludes the talk.
Thanks, everyone. This has been a fun time.